Swayam Prabha. Digital India. Educated India.
Okay, should we start? See, we'll begin from the point which we left yesterday, and what we did yesterday was to arrive at the temperature profile under the conditions of dry adiabatic lapse rate. And then the important relation that we came up was and then we also saw that what it really means in terms of the stability of the atmosphere and whether how the pollutants will disperse, or the atmosphere could be unstable, stable, depending on what is DALR. Okay, this also we call this as the DALR. Okay, but then we also had done a little graph here to show what will be the effect of the moisture. So I will once again write that one. Suppose your air is not dry, but it has a moisture. So let's call the Cp hat that we were describing yesterday with the moisture. So the moisture content is, let's say the fraction is W. So 1 minus W is your air component. So that is air, Cp air if you like, and we put hat, plus W, that is a fraction of water content in the atmosphere, okay, times Cp hat of water, or basically water vapor. So you will see here that Cp dash or Cp hat dash is greater than Cp hat air, okay, or dry air. Therefore, if you recall that the graph which we showed yesterday was Z on this side, T on this side, and then we got, this was something like our reference, okay, and then where will the atmospheric conditions which is having some moisture will be somewhere here. Okay, after considering the moisture, okay, the graph between Z and T will be like this. So this is normal your DALR, okay, and this is, okay, this is a condition when there is a moisture in the air, moisture. Okay, this will depend on the local conditions. Okay, so this what is the thing which I wanted to make this thing clear to you, because we really rushed through this graph yesterday, and then and the other important thing which we came up with was if ELR greater than DALR, what did he say the atmosphere was? If ELR, the environmental lapse rate, is greater than DALR, what did we call that as? Unstable. Okay. Okay. So this is unstable. There is another name given to the same condition, is what we call as super adiabatic. Okay. And we also call this situation and we call it neutral or adiabatic. third situation where ELR is less than DALR, we call it stable or subadiabatic. Or so this is what we did. Basically, I have just summarized as to what we did yesterday. Okay, we'll stay with the same concept. Okay, but we'll see that how these things varies with different hours of the day. This is a typical situation we have talked about. But let's say what happens to my ELR, because that's what I'm interested in, with respect to the various hours of the day. Let's say what happens in the morning. Because you recall I made a statement yesterday that the atmosphere or the environmental lapse rate is not the same always as the DLR. In fact, the ELR will be equal to DLR on a very seldom situation, very rare situation, or very few times, like. So if let's see the situation as to what happens in the, let's say, in the afternoon 2 to 3 p.m. Okay. Situation is, like, say, bright day, and time really we are looking at is, let's say, 2 p.m. to 3 p.m. And then we plot the same kind of graph again. We have Z here, and we have the temperature here. Okay, and my standard lapse rate DLR is like this. Okay, will at this particular time of the day, we'll try to at least say qualitatively how our environmental lapse rate will be there. To draw that one, okay, let's a little bit consider that on the surface of the earth, in the daytime, short wave radiations are coming, okay, and then long wave radiations go out, okay. So what happens at this situation in the bright day, lots of heat coming in, and then first thing happens, earth is heated up. Second thing what will happen is the air adjacent to earth also gets heated up. Air adjacent to earth also heated up. So you will see, as a result, you will see the gradient of the temperature. Temperature will be higher here. As you go up, temperature will be lower and lower. Okay. So if you agree with me, in the daytime, 2 p.m. to 3 p.m. on a bright sunny day, my situation in general is likely to be something like this. Okay. Because at the ground, temperature is higher. As I go up, temperature will be less and less, and reduce much faster than what it will reduce, okay, in the situation of DLR. So this is what will be my ELR. Okay. It is something like, it's the same thing what we said yesterday, the beaker, okay, and you are heating it up from the bottom, and that will give you a temperature profile which will be like this. Okay, and this is my height Z, and this is my temperature T. Okay. This situation has few meaning for us. Okay. If this is what is the situation, if I want to look at the vertical movement of the air, how this will be? There will be strong convections going from ground to up, because you have the higher temperature here and the lower temperature here. So I really look at the wind profile, okay, and the wind, okay, you will see the wind because of the convection, you see the air moving up. Okay. Convective movement. Okay. And this situation, don't forget, wherever I am drawing the graph, is always Z here. This is not the Z, but this is the Z here, but not showing the temperature, but the and what you see during the daytime, especially the bright sunshine, and you can see all the birds flying and soaring very nicely in the air. Okay, that happens in the afternoon, bright sunshine. Okay, because of this, the convective movement of the thing, the birds can really support themselves and they can just soar around without really flapping their wings. Okay, this happens because of this situation. The second thing, another example, just for sake of physical understanding, you see those people who go for hand gliding. See, they cannot go every day. They have to really wait for the bright day, bright sunshine. Okay, and they normally like to go in the afternoon or something like about 12 o'clock or so. They can't go very early in the morning, because even those who go for the hand gliding, they are to a large extent they are supported by these convective currents. Okay, so that they can go this. And then suppose you plan for your picnic or your hand gliding, and you find the day was not very bright and there were the clouds. So once the cloud is there, this thing is cut off. Okay, so earth is not heated up, so air is not heated up, there is no convective currents, and then you will probably put off your plans of hand gliding. You can't do the hand gliding on that day. So the point which is there is when even the birds and your picnic plans can change, so is the pollutant also will depend a great deal how they will disperse, where they will go, depending on the time of the day that we are talking about. And also don't forget, we'll probably talk at some other point, the important word which I am writing in somewhat non-technical term, bright day. It will also depend the amount of the solar radiation that is reaching on the earth. Okay. So what you see here, there's a lot of meaning in terms of the day which we are talking about, in terms of the time we are talking about. And this thing is what we can say is the conditions will be unstable. And you will see, if I can draw a chimney, you will see the chimney, we will talk about a little bit, really dancing and looping and going up and down kind of thing. Okay, this is the emission which you are talking about. Now I take another reverse picture of this one, and let's see what happens in the night time, and we'll draw another picture and talk about that what happens in the night time. You will never see birds soaring in the night time, cannot happen. Okay, so if I draw a very similar picture, T here, Z here, and this is my standard conditions. Okay, go back to the earth. Okay, no solar radiation. Okay, what would happen? On situation we are talking about is night time. Let's say we are talking, let's say between 4 a.m. to 5 a.m. Okay, so there is no solar radiation coming in. Earth cools. So is the air adjacent to earth. Air adjacent to earth also cools. Okay, and then what happens was earth is cool, the temperature here is low, and what is temperature up? Temperature is higher, because adjacent to earth temperature has cooled down, but the temperature over the earth, over the higher altitude, is still high. Okay, this happens because of one fundamental reason. Always remember this: earth cools off very quickly and earth heats up very quickly. Okay, whereas the atmosphere will show some kind of resistance in the change in the temperature. Okay, so what you find, the earth has cooled down, but the temperature is still high. So this temperature is reduced, whereas upper temperature are still higher. So what you get here is a picture which might look like something like this. It's complete reversal of the temperature gradient in the night time and in the daytime. Okay. So this situation where the temperature, instead of decreasing, starts increasing, that is what we call as a temperature inversion. This situation when temperature increases with height, okay, this is what we call temperature inversion. Or some people will call it simply inversion. And more technical name for such a situation, okay, which is, the earth is subject to cooling and heating, is called radiative inversion. Okay. So what I did with these two things, what you see here, is I have talked about very extreme conditions. Daytime, bright sunshine, rather night time in the morning 4 a.m. to 5 p.m. Okay. Let's see what would happen on the other days. It is a situation which, if you like, it is something like this, that you had a beaker with a hot water in there. I brought another container with the cold water. Okay. So you see here, this water will be immediately become cool and this water will stay hot. So the temperature profile, what you will get in this situation is exactly like this. And this is the hot water to start with, another container with cold water. So idea here is to show you that how the things can change from day to night, and we will try to draw an overall picture based on this thing, because things are not as discrete as you see, things are continuously changing. So this is important from air pollution point of view, because all the air pollution that will depend, the dispersion or the vertical movement, always remember these lectures are focused on the vertical movement of the pollutants. Okay, we are not talking about the horizontal movement. So here again we have Z here, T here. Suppose I talk 4 a.m. You see the picture is like this. Temperature, let's write it here. By the time the morning, 9 o'clock, there is a little change as to earth gets heated up and the temperature start becoming like this. Things will change from inversion to we will go this side. Okay. By the time you are around 2 o'clock, situation what we saw a little while ago, okay, and now if I have to draw the temperature profile at 4 o'clock, where do I draw the line? 2 p.m., 4 o'clock, do you think I will be coming onto this side or I will be going onto this side? Here, I move to the left or move to the right? Move to the left, because the heating is somewhat reduced. Okay, so I am getting a reverse phenomena at 2 p.m. or 3 p.m. Things had peaked in terms of instability, things had peaked in terms of the super adiabatic conditions, and now earth is now the sunshine is reducing, as a result the temperature is reducing, and slowly I will start a reverse trend, and then probably if I am at 4 o'clock, situation will be like this. Okay, and then I am still going with respect to time, because why we are discussing this, we all will use this somehow or other. Okay, because you see, we want to find out the concentration, you want to find out the vertical movement of the pollutants at different times of the day. Okay. So now something like when you are close to around 7 o'clock or so, you will be again very close to what 9 a.m. is, and this is your 7 p.m. Okay. And then situation from 7 p.m. onwards, you will get to a situation which is 4 a.m. And this is where this window, what you see at around 9 o'clock in the morning or around 7 o'clock in the evening, okay, this is where things you are very, very close to the dry adiabatic lapse rate, our standard rates, somewhat close. I mean, on a typical day, on a particular day things may change, but this is what will be the situation on typical days. Okay. So this is what is your comparison to. You see here how the things can change, and largely this change is again because of the heating of the earth, the cooling of the earth, and corresponding change in the atmospheric temperature or the air temperature, which may not change as rapidly as the temperature of the earth changes. Okay. There is a question for you. Suppose you want to see the dispersion of the pollutants not on the surface of the earth, but you want to see the dispersion of the pollutants from a chimney or ship. Okay. You have seen all Titanic and things like that, huge chimneys, and they burn a great deal of fuel and things like that. And that is moving on to the, not on the surface of the earth, but on the surface of the ocean. Okay. And then obviously the same kind of stability which you are talking about here, okay, same kind of temperature profile which you are talking about, it will be different, right? Because earth's surface behaves differently, the water body will behave differently. And then again, water body, the problem or the good thing or bad thing about the water body in terms of the temperature, it also resists the change in the temperature. It doesn't get cool off so easily, so they will be delayed. You know, like suppose you are getting 4 p.m. like this, okay, the ocean will, for ocean, this profile will be maybe still at close to 2 p.m. Okay. So that change is very slow. Okay. So that kind of stability will be very different than what you get onto the earth's surface. So this picture is very important for us. Still we have talked about in some sense the qualitative way, but you can kind of appreciate that well, our pollutants will behave very differently as to where we are. We might be here, in the morning they may behave differently, 9 o'clock they will behave differently, 2 o'clock different, 4 o'clock different, 7, and it is a continuous scale. Okay. So we need to know about this information and the stability part. So if you like, I can write this part as unstable and this part as stable. So atmosphere is stable during this time and unstable during this time. Okay, let's talk about something more which will decide. I want to come down to the specific pollutants rather than. Now let's see, let's leave the atmosphere for a while and let's talk about the pollutant. Okay. How the pollutant will behave? Will it go up, down? What will happen to the pollutant? So I draw a picture, again Z versus T. Let's make it a nice one. And Z here. This is my reference DLR, and suppose I am talking what happens in the daytime to the pollutant. We talked about the temperature, but now I want to say what will happen to the pollutant, and let's say the situation is like this. Okay. So situation already we are talking about the daytime, something like daytime, let's say 2 p.m. Okay, and we'll talk about the pollutant. Okay, suppose I have the pollutant here. Okay, which is a small pollutant. Okay, what I did, the pollutant somehow I gave a little push to the pollutant. Okay, what we did, through the chimney you are sending out a puff. okay, the puff went up, okay, and then let's examine after a certain distance it has traveled, okay, what will happen to the temperature of the pollutant and the temperature of the air surrounding this one. That's what we want to examine. So when the pollutant goes up, okay, you can assume that pollutant will travel, or the temperature profile of the pollutant will be adiabatic, okay, because we are neither supplying the air to the pollutant when it came out, or not taking the air out for a short duration for which we are considering which. Something similar what we derived the expression yesterday. So what will happen? This is your actual, if I can use the word actual. So the pollutant will, although traveling vertically, but the temperature profile, it will be following the dry adiabatic lapse rate, because this is important. If you miss this point, okay, then there could be confusion. So after a certain time when I have pushed it up, what temperature it will acquire? Suppose it has gone up to this point, okay, so it will acquire this temperature because it will follow the adiabatic path, whereas my atmosphere is real like this, that's fine, but the pollutant will follow adiabatic path. So let's say after some situation the pollutant is here, let's say. So we pushed it up and it acquired this position, that I call as situation 1, okay. Corresponding to this, the temperature of the pollutant, let's call that as Tp, okay, at situation 1. So this is the temperature of the pollutant. What is the temperature of the air surrounding the pollutant? So that I have to you agree that this will be the temperature of the air, because this is my actual air is like this. So let's call this as T air and at position number 1, okay. So what can you say is the pollutant, what will happen to the pollutant? Now you have to answer the question whether the pollutant will stop here, or it will go up, or it will come down. It will continue to go up, because what it finds that surrounding air is cooler and the pollutant temperature is higher, okay. So situation number 1, so we do situation number 1, okay, what we have kind of concluded is Tp1 is greater than Ta1, and the resultant or answer is pollutant go up. You made just little push, okay, and then it continues to go up. No matter what height I go, it will still continue to go up, right? Okay. What is the situation? Suppose I pushed it down. So when I push it down, it should follow the adiabatic lapse rate. So it comes to the situation which is situation number 2. That's situation number 2. Okay. And then the corresponding temperature of the pollutant is, let's say this is what T of the pollutant for situation 2, and what is corresponding temperature of the surrounding air? This is T of air at point 2. Suppose the pollutant, we push them down, okay. Situation 2, what I can say, T of pollutant at situation 2, T of the air at situation 2, temperature of the pollutant is less, okay. So we make it like this. Okay. What will happen to the pollutant? It will continue to go down, okay, continue to go down, okay. So what you see here under this situation, the pollutant also is either it continues to go up or continues to go down, and you see a lot of turbulence in the atmosphere, okay, and the particle you can't make it sit at one place, it will move, it is on move. It is something like this. Well, I tried, but it is not very, they haven't done a good job here, but it's something like this, okay. It's an inverted ball, and if there is a ball kept here, okay, it will not be stable, okay, it falls off. If the little tilt, it will fall off this way, that it may go up, or it may little tilt this way, it will fall off this way, okay. So what you see, the pollutant either will continue to go up or continue to go up, it is highly unstable. The pollutant is highly unstable, okay. So this is what is the situation, and this is something, if you like, I can put it like this just for the clarity as to the ball is sitting here and it is unstable. It is willing to fall or is going to fall quickly this way or that way and continue to move, okay. So situation is unstable, and in unstable you see the pollutants will be traveling, mixing, jumping and things like that, okay. So again, that is what is the thing which I wanted to tell you. Okay, let's talk about situation 2. We have a situation which is something like this: Z, T, okay. My atmosphere is same as adiabatic atmosphere. So I left a particle here, okay, which is again air particle, and I pushed it up to situation 1. Situation 1, and I will try to look at the temperature, okay, TP1, and try to look at the temperature of the air, that is TA1, and you see almost, okay, TP1 equals to TA1, okay. And similarly, if I push it down to situation number 2 here, and then again you will agree with me that for even for situation 2, TP2 is equal to TA2, okay. So what it is saying, you push the pollutant under the neutral conditions, well, it will get pushed and acquires a new position and stop there, okay. So it is not so highly vertical movement, but if you give some movement, it's going to sustain that movement to up to a certain thing, up to a certain distance, and probably acquire a new position where it will be quietly sitting there, okay. So this is what is situation we know neutral, or it is something like this. Suppose there is a flat plate, okay, something like this, and then there is a ball here. So slightly push the ball this way, it acquires a new position, okay. You push the ball this way, it acquires a new position. It is something like if I have the same ball and rolling it over the duster or rolling it over the surface, I pushed it, it gets a new position, and I push it this way, it gets the position. So this is the neutral, and this is what typically you will see the chimneys which are, okay, are like, I mean, dispersing a little bit on both sides and stopping it there, okay. So this situation also you will realize, okay. But plume is not dancing up and down as we have seen in the earlier thing, but you see here nicely traveling as a conical shape of the dispersion that takes place, okay. Okay, now let's talk about the situation number 3, when things are very stable. Z, T, this is my reference rate, dry adiabatic lapse rate, and let me take a really little, this situation, something like this. Let's make it slightly more, this thing. So this is the night time unstable condition, and let's see what happens to the pollutants when atmosphere is stable, okay. So what you see here, the particle is here, okay. I push the particle through a puff, okay, at position number 1, and this position number 1 is here, and as we have been doing, at this height the temperature of the pollutant will be TP1, Okay, and what will be the temperature of the air at this height? Temperature of air, situation 1. Okay. So what do you say? What will happen to the pollutant? It will come down, and come down to what level? To its original position, wherever it was. So you see the pollutant, even if you had somehow pushed it up, it will come down. Why? Because TA1 is greater than TP1, and the pollutant will come back and stays back here wherever it was started with. Okay, it comes back. Okay. Suppose we have situation number 2. We push the pollutant down, let's say. Okay, this is the situation 2. Okay, and then let's find out the situation. What is the temperature for the particle is TP2, and what is the temperature for the atmosphere or air is TA2. Okay, in the position 2, TA2 and TP2. What is the relation? Are we getting same or different? We are getting the same relation, that TA2 still continues to be higher than the temperature of the pollutant. Or did I say the word? Okay, okay, all right. So situation is like this. Okay, TP2 is higher than TA2. So what happens to the pollutant? It will go back, and it go back and come back and stay here. See? So no matter what you did, you are shaking the things, you want to move this one, but the pollutant, if I can use the word, refuses to move. It says, I am not going anywhere. I will just stay where I am, no matter how much you tried. You see, we tried to push this pollutant from here to here, it came back. He said, sorry, I don't want to go up. You push it down, he said, sorry, I don't want to be down, I want to maintain my original position. Under these situations, it is a situation which is something like this, that you have a ball, in the bowl you put some ball kind of thing, shake this one, and this is not coming out. It just stays wherever it is. So this is something very, so if for the demonstration purposes or for writing this thing, I can make it a ball like this. In the bowl, I make a ball, and then shake it. How much the energy I try to give this one, it is not moving. So things are stable. Pollutants don't travel, don't disperse vertically. They refuse. Okay, that situation is really very bad. Okay, and that you can say that will happen in the what time of the day? Night time. Okay, this is something you remember. We draw this picture. Something this was at 4 a.m. Something like this. Okay, and that is what exactly. If you recall, there were more deaths in Bhopal episode of Bhopal gas tragedy, because it happened in the night time, and situation was something like this. There was no dispersion of the pollutant, the vertical dispersion, and then as a result the concentration will go up and more people will suffer. Okay. So if you see how the chimney will disperse, well, we'll talk a little bit more in details these things, but you see here, as the pollutant refused to move, the chimney will simply, you can almost draw a straight line. There is no dispersion, no vertical movement, and the chimney will just be like this, and it can travel hundreds of kilometers until the day breaks and situation change. Okay, this is what is highly stable. Okay, but you see, the advantage here is that the people at the ground level are not so much affected. So in a way you are saying stable conditions are bad, but if the source is elevated source, the problem faced by the people is not so bad. Okay, but just imagine if the source was the ground level source, okay, the ground level source, and you see this will not disperse, as a result the entire population will be affected. This is the ground level source. So that is how you see in the night time, in the winter, in the evening, there's some source which will cause some kind of layer, and that is not dispersing. And you see the pollution level really going up. So if there are vehicles, they create a lot of problems. Okay. Interestingly, I mean, sometimes people don't recognize this. In the winter, okay, in the winter and in the night time, the problem from the tall stack may not be so great. Okay, because you see the pollutants are not dispersing. So they are not coming to the ground level. If it is not coming to the ground level, it is not affecting the receptor. Okay, there are other issues with this one that we will see, because the other issue, what will happen to this one when it is not coming out, then it will be subject to long range transportation. And once the long range transportation happens, we all know the problem of the acid rain, problem of the places being affected from very far distant locations. Like the Norwegians would shout, well, the emission is from Germany, or this emission is from England. Okay, the Canadians will shout, the emission is from this thing. So they have a situation which is like this. Okay, in this kind of dispersion. So you see here, what we have done in this lecture is that we started with the atmospheric stability, okay, and said that stability varies depending on the time of the day, and that concept of stability, we took it from the atmospheric stability to what impact it will have onto the particles or the pollutants, and then how the pollutants can behave. Okay, that is what we try to do so far. Important things, and somehow or other will utilize this thing. So since time permits, we will also like to do something else. Now what I want to draw is to see how temperature profile of the entire atmosphere or the entire vertical atmosphere with respect to various time of the day. We had talked about very limited thing, okay, but let's say if we are talking about the whole thing and how, we are talking, let's say something like 2000 meters or so. This was with little local things we are talking about. So now if we are talking about the bigger things, okay, something is at here, okay, let's say approximately I put this as 2000 meters and the temperature. Okay. So how will be the profile? Now you are knowledgeous, you can tell me. Let's say I start in the morning 4 o'clock. So what will be the profile? Increasing temperature with height. Okay. So generally you do get a situation through the entire region. Okay, you get something like this. Okay, can you comment, okay, or at least make a guess, what will be the profile after a certain height, let's say 2000 or 2500 meters? Will it be continue to be like this? Or it will have some change or shift? It will change, because the influence of the earth will diminish as you go up. This particular profile you are getting, why are you getting this particular profile in the night time? Because there is an influence of the earth, cooling of the earth has resulted in decrease in the temperature, and that influence will be up to a certain extent, and the influence will diminish as you go vertically up. Okay. So generally it has been found that when you go up that particular height or so, will define what is that height. So if the impact or the influence of the earth is diminished, what kind of profile you expect? Ordinary normal profile, the temperature decreasing with respect to height. That we all know the temperature at the Shimla will be lower than the temperature in Delhi. Okay. This is what we have seen, and what we have, the conclusions draw is that of the influence of the earth. So as you are going up, the influence of the earth is diminishing, and you might get a situation which is again something like this. Okay, even in the night time, okay, even in the night time, you will see the thing will not be so sharp as I have drawn here, but something like this. Okay, you agree with this kind of profile, or you think this cannot be? Influence of the earth will diminish, right? The normal behavior of the atmosphere is this. Okay, but since it is getting influenced by the earth, okay, so that's why there are changes at the local level and things like that. But at the higher altitudes, I just put the number 2000. don't take this number as a very sacrosanct. 2000 means something like this happen. It may happen at 2500, it can happen on 1500, depending on the year or depending on the day of the year, winter, summer, these things change. But I just want to give you a feel that things can change. Okay? This is what typically, if I send out if I start measuring the temperatures at different heights and go beyond 2000, I would get a picture something like this. Okay? And this is what normally I've drawn at 4 o'clock, but normally at 5:30 IMD, that is, what is IMD? Indian Meteorological Department. It is, yeah, that's correct. So what they do, in fact it is the India Meteorology Department, okay, not Indian, interesting. Okay, so what you see here, they every day in the morning, 4 a.m. I have written, but they normally send a radio sound, okay, in which they send a balloon up, and then with the balloon remotely they can look at or they can with their computer they get the temperature at various heights. Okay. So standard thing to do is 4 o'clock I wrote here, but standard thing what IMD does is probably they send it at 5:30 a.m. and they do get some profile like this. Okay. And for IMD now of course things are very easy to do, but it is still difficult to get the temperature profile for every hour to hour and minute to minute. Okay. So now let me pay some attention. Okay. Let's say now I'm in the morning 7 o'clock, okay, or let's say 8 o'clock if you like it. Okay. I'm here 8 o'clock. What will happen? My temperature will increase or decrease? Compared to 5:30 am, temperature will go up. So I am somewhere here. Let's say at 8 am. Okay. Do you think this profile of the temperature, okay, the temperature is gone up, that is for sure. We all know that one. What do you expect? This profile to be like this, or the profile might slightly change? Profile will change. It will slightly change. And then you may get a profile to be something like this, because earth has got heated up, the surrounding air also got heated up, okay, and you see here the profile at 8 am becomes like this. And so I will probably you can write it differently at different times. So if I go and measure the temperature at 8 o'clock, the vertical temperature, this might look like this. You agree or disagree? I think this is, you will agree with this one, that if suppose I go and take the profile in the morning 8 o'clock, things will change. Okay. Okay. Then let's say I went at 11 am. Okay. Then things will change. There will be some slight this thing, but something shape will be, because by the time 11 o'clock temperature is even higher. Okay. And then you will see here at 11 o'clock the picture will look like this. Okay. So you see at the elevated levels, okay, inversion is there, but at the ground level inversion is broken. Okay. Okay, you see this thing? What a interesting thing. Okay. And by the time you are like 2 p.m. or something like this, temperature is even higher. Okay. So you may get a situation which is complete disappearance of the inversion. Inversion is completely gone. Okay. So this is what you see at various time of the day. Okay. And what will happen? There will be a reversal trend as the sun sets, right? You will get back to your changes here. From 2 p.m. you will get 4 p.m., 6 p.m., 7 p.m., 9 p.m., 10, 12, 5, 5:30. And you will see here the things are changing. So what you see and how the behavior will change. So what the thing which I am trying to, if we can reconstruct that thing, and if 5 o'clock it was like this, 6 o'clock it was like this. Or why don't we do one thing? Quickly. Alternation movement. So this is a picture at 4 a.m. This is picture at 11 a.m. Okay. Well, I've occupied the all space, and this is a picture. But don't forget, we are talking about ZT. This is the picture which you'll get something like this at 2 p.m. For this thing, what I want to point out to you is, depending on where your source is. If your source is here, the dispersion will be different, right? If your source is chimney is here, the dispersion will be something else. Okay. So, and if your source is here, things will be different. Okay. And that, depending on this layer going up and down, your dispersion or your chimney will vary or will change. Okay. And that is what we want to somehow model that as to how these variations will be there. So sometimes your chimney may not disperse, because if your chimney is sitting here, okay, you will say, oh sir, this is a bright day, sunshine, and we see the chimney is not dispersing, because chimney or your stack is trapped in this one, and here the dispersion will be very, very poor. So you see what you have seen, this variability in the temperature profile with respect to day or stability, in meteorology we call this as diurnal, that is daily, diurnal variations. And you can appreciate, we are not talking about mathematics as yet, but you can appreciate what these things would mean when it comes to the dispersion of the pollutant, because we ultimately, what we want to do, want to look at the source and what is the impact onto the people, how much it is dispersing. Okay. So we'll stop there. If there are questions, we talk about those. Otherwise we stop there, but you should have a good feel of the things now, how the atmosphere behaves, how possibly pollutants can travel, and what possibly could happen to them, at least in qualitative sense, if not in quantitative sense. We'll stop there. Thank you very much.